Are you ready for more punishment? If so, I guess you are, because that's why you started playing this video. I'm going to give it to you. The next functional group that we can talk about is an ether. An ether is very similar to an alkyl halide. That's kind of why we like to follow up the alkyl halide description with ethers, because they're very similar in how they function and how they cleave. Only difference is that it's the functional group itself. So, review of organic chemistry, or maybe some infrared. An ether is an ROR group. And remember, R's can stand for any random alkyl group that they need to be. So, for instance, CH3, CH2, O, CH2, CH3. Right? That is an ether. But they don't have to be the same. CH3, CH2O with a CH3 on one side. That's also an ether. It's an oxygen sandwiched in between two carbons. That's all that it is. The top one is called diethyl ether, or ethyl ether for short, or ether for even shorter. That's the common ether that we always have in the laboratory, and it's sometimes also used as a, back in the day, as a anesthesia. So we would put it on your mouth and you would suck it in and you would pass out kind of like chloroform, and nobody will ever be the wiser. They could chop off your leg and you'd never know about it. You'd wake up with a headache and a missing leg all at the same time. All right, so that's the ether functional group. An ether will cleave. So let's say that we have ROR. An ether can have the possibility of cleaving on that side. And if they're different, it could also have the possibility of cleaving on that side. No big deal. We would kind of do that anyway through the normal thought process of getting these fragmentation patterns. I mean, that would kind of be something that we would expect. The oxygen can take all the electrons and it can go away. And the positive piece goes on the other side. All right? Again, keep in mind, chlorine and bromine are very electronegative. Well, you know, oxygen's electronegative as well. So if it does cleave on this side, and I'm going to get rid of the other one for now. We'll do that separately on a different line so we don't get confused. Let's say it cleaves to the left. Oxygen is electronegative. So this is the piece that gets the negative, and the remaining piece over here will get the positive, and this is what gets picked up by the mass spectrometer. All right, well, if we had this other option, let's say that these are not the same group. That's why I keep writing the prime up here at the very top. That's different. We can cleave it on that side. This will get the negative piece, and away it goes. Oxygen's electronegative. It doesn't get seen. And what we have left over is the positive, and this is what gets seen by the mass spectrometer. If the molecule cleaves this way, simple, clean cut, nothing fancy, oxygen gets negative, goes on the other side, that's the positive. This is what we call the heterolytic cleavage. Imagine that. Same kind of thing happened with chlorine and bromine, right? We said that if these were attached to a molecule, we cut it, away they go. What we have left over is the positive piece. Same thing's happening here. Only difference is that oxygen's going to carry part of the molecule away with it. In the alkyl halide case, it was simply just the chlorine or just the bromine. But here, oxygen's got some part of the molecule attached to it on one side. So that oxygen's going to cleave, that gets the negative, and it's going to take with it everything else that's on that side once it cleaves. That's heterolytic. There's also kind of a statement that I want you to burn in your brain down here at the very bottom. The most stable fragment is the one where oxygen gets attached to the bigger piece in a heterolytic cleavage. So we have these two options. We will always have these two options. Oxygen can cleave to the left. Oxygen can cleave to the right. We're going to get these fragments no matter what. We're going to get them. We're going to see them. But one is going to be preferred over the other. And this is how we determine which one is the preferred guest at the hotel. Is it this one or is it this one? What I do is I look at this oxygen and I give it to the biggest piece. And what I have left over is going to be the most stable fragment. Now, that's only one option. Alkyl halides, we said heterolytic cleavage was option number one, but we also had something called a homolytic cleavage. Well, guess what, people? We got homolytic cleavage in ethers as well. What do you think it's going to concern? It's going to concern the alpha carbon, just like it did in alkyl halides. All right, so CH3, CH2, O, CH2, CH2, CH3. Here's my ether, and now we're talking homolytic cleavage. Homolytic cleavage, just like with halogens, focuses on the alpha carbon. All right, so that's the carbon that's directly attached to the O. So here is the alpha carbon, but you know what? I've got an alpha carbon right here too, because that's also attached to oxygen. By definition, it meets it. So two alpha carbons here. In a homolytic cleavage, what happens is that the electrons are pulled away from the alpha carbon. And it allows the cation to stay on the oxygen-containing piece. Think about it. Halogens did the same thing, right? We cleaved it. Those electrons moved in, and it created a double bond between the halogen. And that's what gave it a positive charge. Ethers are going to be the exact same way, people. There's no difference. All right, so I'm going to actually draw an ether. We're going to kind of get to the bottom of this for a minute. And this ether I'm going to draw is going to look pretty complicated, but I'm doing it on purpose because I want you to kind of understand it's not really the entire molecule as a whole. What this is really just one area of the molecule that you have to place a focus on. So here's an ether. The left hand and the right hand sides are different. So it's not a symmetrical ether. So this molecule goes into the mass spectrometer, and the molecule gets hit with the electron beam, and away an electron goes. This ether has an option to cleave. All right? What it can do is that it can determine, because it's not symmetrical, it can determine in route number 1 to cleave on this side. When it does that, what I have is a CH3, CH2, CH with a CH3, and then I have this oxygen piece with these 3 carbons on it. If that bond breaks, these are my 2 options. The oxygen will get the negative area, so I'm putting a negative there, and the piece to the left-hand side will get the positive, and that will be seen by the detector. This will not be seen by the detector because that's a negative. It will get sucked out. Next up, this ether also has the tendency to cleave on the right-hand side as well in the heterolytic cleavage. If it does that, then we will see a CH3, a CH2, a CH, an O. Let me get rid of that scribble just so it doesn't confuse you. And then a CH3. On the other side, I'll have a CH, CH3, and a CH3. So it's cleaved at this point. There are my two halves. This gets the negative because the oxygen's electronegative, and away it goes, and this will not be seen by the detector. On this side, though, that will get my positive charge, and this will be seen by the detector. So what would happen is that if I looked at the fragmentation patterns here, this fragmentation pattern up here at the top would give me about 116. I would see that signal. If it cleaves to the left, well, this one will never be seen. This will be my positive piece that will be seen by the detector, and this will give me a signal of around 57. 12, 12, 12, and 12 is 48, 49, 50, 51, 52, 53, 54, 55, 56, and 57 from the hydrogens. If it cleaves on the right-hand side, well, these are my two pieces. The oxygen gets the negative and goes away. I have this positive that's left over. This fragment will be a 43. 12 and 12 and 12 is 36, 37, 38, 39, 40, 41, 42, and 43 from the hydrogen in the center. I'm starting to get some peaks, right? Now, keep in mind that we had a statement that said if this molecule cleaves, the molecule tends to be more stable when the oxygen goes to the largest containing piece. Well, if I look at option number 1, this oxygen went away with these 3 carbons. If I look at option number 2, the oxygen went away with these 4 carbons. So it looks like this might be a more stable fragment, meaning that if this is the more stable fragment, then this is probably going to be more abundant when it cleaves in reference to the other option. Now, is that going to be true? We'll take a look at this when we take a look at the mass spectra. We're not there yet because we still have homolytic cleavage that can come along. But this describes the 57 peak that we might see and the 43 peak that we might see. We can already make a determination that probably the 43 is going to be higher. And the reason is because the oxygen is with the largest piece in those two choices. It's bigger, it's greedier, it carries more electrons. The larger fragment can help kind of neutralize that out and make it a little happier without a problem. Now, let's talk about homolytic cleavage. I'm going to use the same molecule up there at the very top. I'm just going to have to redraw it, and I'm going to start a brand new slide because we need some room here to talk about the homolytic cleavage that can happen. So let me clear this out, and we're going to try this again. CH3, CH2, CH, CH3, oxygen, CH, CH3, and a CH3 there. Notice how I've drawn this time. I've really kind of showcased each bond between the carbons. And the reason I'm doing this is because it's going to help me kind of explain what's getting ready to happen in the homolytic cleavage. So this molecule goes through the electron beam just as before. If it doesn't want to do hetero, then homo is an option for it to do. It's going to happen. There's no way around it. It's going to go this route. And we just need to kind of figure out where these fragments or pieces are coming from. Okay? So we said that this homolytic cleavage, and I'm going to write that up here in the top corner. This is the homo version. We'll look at alpha carbons. So this oxygen has an alpha carbon. It's right here. And it also has an alpha carbon to this side. It's right there. Again, those are carbons directly attached to the O. The same definition that we used for halides. the carbons attached to the chlorine or the carbons attached to the bromine. And the molecule can make the judgment to cleave at an alpha carbon. So I'm going to tackle the right-hand one first because that's going to be a little easier. What happens here is that at this alpha carbon, we can make the decision to cut away a bond. So it's not going to happen at the oxygen. It's going to happen at the carbon that's attached to the oxygen. So let's just kind of get rid of this one. There's that sound effect. I know you like that. Okay, so what we have left over, if we do it this route, is the CH3, CH2, CH, CH3. The oxygen is still attached, and that's attached to a CH group, which has a CH3 group on it. So this whole thing is one piece, and this poor little methyl group, this CH3, is off on its own. When that bond breaks, the same type of deal happens that we saw in homolytic cleavage for my bromine and my chlorine. What that means is that the electrons in this bond will migrate inward. And what we would end up seeing is a double bond that gets formed because that oxygen's electronegative. It's electron greedy, right? Remember that. So it's going to take the electrons from this cleaved bond and it's going to move them inward and create a double bond at that location. So really what we have here is a double bonded O to that carbon now. So it gets rid of this piece, away it goes, and it uses some of the electrons here. It moves them inward just like bromine or chlorine did to form a double bond at that location. And now oxygen says, oh crap, I've got too much. I bit off more than I can chew. I spread myself too thin. And it gets, just as in the halogen, a positive charge. And this gets the negative. This is what's seen by the mass spectrometer. It carries the positive charge with it. And if I do all of the addition, 12 and 3, 12 and 2, 12 and 3, 12 and 1, 16, 12 and 1, 12 and 3, what I would end up with is 101 for a fragment. All right, well, I'm not going to go through this again because you know what? Here's the alpha carbon. I'm going to do that in a similar color. We chose to cleave it here up at the very top. Now we can choose to cleave it here. It's not going to change my structure though. Because look, in the first case that we did, it released a methyl group. Off it went. In this case, it's going to release a methyl group. And we have an OCH-CH3. OCH-CH3. It's symmetrical. It's the same piece that's getting cut off. So I'm left with the same piece that's left behind. So I'm just going to say this is times 2. No matter which one I cut, it's going to be the same. All right. Now let's redraw that structure from at the top. CH3, CH2, CH, CH3, O, CH, CH3, and CH3. Again, I'm focused on the alpha carbons here. An alpha carbon is there. An alpha carbon is there. Well, we've already taken care of the right-hand side. No big deal. Right-hand side's taken care of. We said that either one of those methyl groups can be chopped off of there. Gives us the same product in the very end. So we're looking at that 101 peak, and that's it. All right, well, now I can focus on the left-handed alpha carbon. And my first option is to cleave maybe that bond. No big deal. We can do that. So what I have left is a CH3 group, CH2, CH, O, CH, CH3, and a CH3. When this piece gets cleaved off, it's on its own. Those electrons move in and create a double bond, just like it did up here, just like it did in the halogen cleavage. That's the typical homo cleavage that we always see. And when that happens, oxygen gets oversaturated, too many bonds are there, too many electrons are there, and that gives us a positive. And then it could also cleave in a different way. So I'm going to rewrite this structure one more time. And now in this scenario, here's the alpha carbon. We chose to cleave this one up here. Now we'll choose to cleave this one here. That is a different product. It's a different fragment that we'll get. So I get this CH2CH3 that's left behind. I'll write it down below. And then I've got this CH3 group, a CH, an O, a CH, CH3, and then a CH3. These electrons move inward. They go to that oxygen. Again, electronegative. We get that double bond that gets formed there. And when that happens, that gives us the positive charge. That will be seen by the detector. So this is my negative, and this is my negative. These do not get seen. I'm going to cross those out. And if I do the nominal mass weights of this fragment, 12 and 3, 12 and 1, 16, 12 and 1, 12 and 3, 12 and 3, what I would end up here would be a fragment of 87. If I go up here to the very top, that fragment was 101 because we lost a methyl group. If I look at the second option where we started tackling the things over here on the right-hand side or the left-hand side of the oxygen, look, that lost a methyl group. If I did the fragmentation weight, 12-3, 12-2, 12-1, 16, 12-1, 12-3, 12-3, that also gives me 101. Huh. So if it cleaves to the right, I get 101 two different ways. If it cleaves to the left, I also can get 101 from that. And if it cleaves to the left, the second option, I'll get an 87. So there's some numbers that I've got to kind of take away. Now, keep in mind that we did not talk about which one was going to be more stable in the homolytic cleavage. It was just the heterolytic cleavage that we did that with. Now let's take a look at the real mass spectra. And I keep saying spectra, but it's really spectrum because this is singular for this one particular molecule. And here we go. All right. So these are the numbers that we were pulling from the periodic chart or from the fragmentations that we were doing. All right. At least the majority of them. So we just determined where the 101 could come from. This was due to our homolytic cleavage. It happened 3 ways out of the 4 options that we basically gave. So 101 would be fairly high, right? The other option that we did with homolytic was 87. So we saw where that 87 can come from. And if I just minimize the screen down, here's kind of a quick review of where that fragment came from. And it looks like the 87 is actually higher than the 101. So you're probably scratching your head and you're like, well, 101, it just showed up more often. So we were expecting that that would be higher than 87. Well, it's not really due to statistics. It's really due to as far as the fragmentation pattern goes. The molecule, how is it going to break apart? What is the best way for it to do that? Heterolytic cleavage, we said oxygen typically goes with the bigger fragment, right? But at no time did we say that that's what homolytic cleavage does, because this 87 is higher, but the 87 is not the bigger fragment. What's kind of happened here is that the molecule has looked at this piece, because this is getting the negative, right? And it looks at this poor little methyl group on these cases, and it says, are you a big enough boy to take care of that negative on your own? And the molecule just doesn't feel comfortable with that. It actually feels more comfortable giving a negative charge to that larger fragment, CH2CH3 in this case, and that's why 87 is a little bit higher than all of these choices of 101. But that's where the 101s are coming from. Now, we also kind of discussed the whole possibility of how it got the other fragments that we're seeing here. So I've already erased that on my slide, but guess what? I've got one right here. So this was the very first one that we did, which was the heterolytic cleavage. And we said in option number 1, we could get a 57. In option number 2, we would get a 43. And if I go back to this mass spectrum, that's where the 57 and that's where the 43 is coming from. So the 47 or the 57 and the 43 is coming from the hetero version. The 87 and the 101 is coming from the homo version. The 116 is going to be the M peak. And you know, this one, is that really an M plus 1 peak? Is this an M plus 2 peak? We really can't tell because that number is not given to us, and we don't want to make an assumption. So unless they give us that information, we don't want to take that further step in trying to determine what that is supposed to represent. Okay, again, we see this one random peak that here is at 41. And at 41, we don't really have an option on how this was created yet, right? And that's not what I'm focused on right now. We're looking at major peaks, ways that these things can cleave. We've identified the majority of them, not every single one of them, but we've identified the majority of them. And that's all that matters. We're not going to get bogged down in all of the more detail that can come from interpretation of a mass spectrum. It's the same as when we talked about infrared. When we talked about the infrared, we said, hey, we've got like this kind of symbols that can happen in the front, and then the back end, we would see all kinds of crazy stuff. And we said all of these things you don't need to look at. This is the fingerprint region. This kind of helps determine what molecule is what. And even in the functional group region, we did not identify every single one of them. We did major ones. The same thing's happening here. The goal here is not to identify every single peak or signal. It's to identify the major ones, the more important ones that we can easily look at a structure and tell. All of these other weird, wonky numbers, they're just kind of weird, and we'll look at those a little bit later on. But again, we can get so much detail that we can create entire semester courses out of mass spec if we want to. All right, so in the next video, what we'll do is that we'll take a look at some of these other example problems. So here's one of them, and it says the mass spectra of 1-methoxybutane, 2-methoxybutane, and 2-methoxy-2-methylpropane are shown in figure 12.7. Match each compound with its spectrum. So this is where we're going to stop this video. And in the next one, we'll pick up with this example problem. We'll draw these structures out, and we'll try to match these mass spectra to the proper compounds.